So, good afternoon, everyone. At first, I'd like to thank Dr. Hamzi and all the other organizers for the opportunity to present this talk today. This talk is a joint work with Professor Hector Zeno, and it's about a question that sounds simple and turns out to be really hard to test. When a language model answers a few-shot prompt correctly, has it inferred the rule behind the examples, or retrieved a surface pattern that happens to fit? The difficulty is not a shortage of models, it is the absence of a reference. On almost every benchmark, we have the intended answer, but no account of what the evidence licensed. We supply one exactly. We fix a minimal Turing complete machine, enumerate every program up to a length budget, about 86 million of them actually, and compute the exact posterior under a declared bounded prior. Then we score 105 serving configurations against it. So, in-context learning is the ability of a simplest model to infer a test from a few examples in its prompt and generalize this to a new query. It is among of the most consequential capabilities of modern language models and among the hardest to interpret. Show a model three examples and it answers the fourth correctly. Two very different stories explain that. In one, it inferred the rule and applied it. In the other, copying the most recent output happened to work here. On a single item from the outside, those look identical, and the obstacle is definitional as much as empirical. On most benchmarks, there is no agreed account of what the examples license, so behavior can only be compared against other models or human answers, never against an explicit posterior. It's worth saying what the adjacent literature supplies. Algorithmic reasoning suites such as ARC or CLRS probe rule induction and execution, but they score against the single intended answer. The theory connecting in-context learning to Bayesian inference and language modeling to compression does compare against posteriors, but to stay tractable, it uses non-universal classes like linear functions, parametric mixtures. So, closest to us in this work, the meta-training networks on data from a universal machine. Their machine is a close relative to ours, but they sample programs rather than enumerate them. And sampling leaves the target out of reach, so their baseline is a loose upper bound on the log loss rather than a posterior. And the mechanistic accounts describe how models update in context, not how close to the updated lens to a designated posterior. Let me build the reference site from first principles. Solomonov's answer to what we should be inferred from data is put a prior over programs weighted by description length and do base. Short programs get more weight by a factor of 2 for every bit saved. The algorithmic probability of a string is the total prior mass of the programs that output it. That take as your prior, and the resulting predictor is a base optimal. For the declared generative law, none achieves lower expected loss. Levin's refinement adds a code for the halting time, making the mixture computable rather than merely definable. The obstacle is equally famous. It is uncomputable in general and expensive when bounded. Enumerating small machines has long been used to estimate complexity numerically. What had not been done is using such an enumeration as an exact inferential standard for a learning system. Here is what we do in actually 4 steps. We fix a minimal Turing complete machine, a 5-instruction tape automaton we call F. We then exhaustively enumerate every valid program up to 13 instructions, about 86 million of these programs, weighted each by a bounded Levin-Solomonoff prior. Because this enumeration is exhaustive, behavior to prior mass is a sufficient statistic, so the posterior predictive for any few-shot context follows in closed form, and nothing tuned to the models. And fourth, the part people ask about. Models are never told the reference exists. The prompt says one fixed program generated this behavior. It does not name F, state the prior, or disclosure the budget. So the score reads the inductive prior the model already encodes. This is base optimal for the declared bounded prior, not universal Solomonoff induction. So, the part one of the paper and the presentation is to describe how the instrument is built. Everything downstreams depends on the target being exactly what I claim it is. So this is our reference machine, F. 5 instructions on a bit tape preloaded with a binary input. Left and right move the head and abort if you run off the tape. Plus flips the bit under the head. The brackets are while the current bit is 1 loop. The only validity test is bracket matching, and the output is the bit string on the head exertion window at halt. It is small enough to enumerate exhaustively within a length and runtime budget, and expressive enough that its short programs realize counting, arithmetic, and bounded recursion. On the right is the complete trace. A program, right, flip, left, on input, 1, 0. Step 1 moves right, step 2 flips that cell to 1, step 3 moves the back to left, and the counter passes the last instruction, and it halts. The head visited 2 cells, so the output is 1, 1. Now the step that makes everything exact. We run every enumerated program on a fixed order input set and record its behavior, meaning the tuple of outputs it produces. Then we sum the prior weight of all programs realizing each distinct behavior. That table is a sufficient statistic for Bayesian inference over F prior restricted to those inputs. Nothing else about the programs matter. Here is a time instance you can check by hand. 155 programs realizing 29 behaviors, and 106 of them never halt, which is the largest single block of mass. Note the weighting on the right. One length 1 program carries 32 times the weight of a length 3 program. The prior concentrates hard on short programs, which is why summing over lengths is exact far beyond full precision. With the table in hand, the posterior is a 2-line calculation. Call a behavior consistent if it reproduces every shown pair. The posterior predicted for a query input is the prior mass of consistent behaviors producing a given output there, divided by the total mass of consistent behaviors. No sampling, no variation or approximation, no estimated baseline. 2 consequences here. When texts are drawn from the bounded F prior, no predictor attains lower expected log loss than this, and a scope condition are returned to in part 3. Our evaluation sample is curated from that prior with quotas over length and complexity plus learning gates. So this is space optimal for the prior and not for the curated evaluation log. That is the single most important caveat in this whole approach, and we quantify it rather than hide it. So let me make that concrete on the smallest non-trivial case. The hidden behavior is the one from the previous table, and the query is its output on the empty input, whose truth is double 0. With no examples, the posterior is dominated by non-halting at 56%, with the truth at 19. That is the prior speaking. Review one example, and the posterior collapses to a point mass on the truth. One example spins the program, so this test has Bayes sample complexity 1, and every induction test carries that tag, which gives us a per test difficulty scale. Now, watch the pattern completion foil in the last column. At the 2 examples, it has 2 different outputs. It hedges between them, and it pays about a bit of regret while the reference pays none. That is the signature we hunt for in the models. One more construction before we can trust the target. The tape starts all 0, so zeros are cheap, and the raw prior prefers 0 heavy outputs. The probability that the first output bit is a 1 is one more construction before we can trust the target. The tape starts all 0, so zeros are cheap, and the raw prior prefers 0 heavy outputs. The probability that the first output bit is a 1 is 0.278, not a half. A frozen benchmark carrying that bias would quietly reward models that share it. So we do not merely note it, we remove it exactly. All references are served from the complement symmetrized machine, and every test shifts its bitwise complemented twin, on which the reference provably scores identically. That buys 2 things: a provably polarity-neutral yardstick with a first bit log of exactly 1/2, and a free diagnostic. The polarity gap between a test and its twin is exactly 0 for the reference as for any complement equivariant predictor. So a non-zero value is attributable to the model alone. Measured, the median model gives the complement answer on the twin tests only half the time, so most of the panel lacks that equivariance. A benchmark whose targets from a bespoke GPU accelerator invites the obvious worry that we are measuring the accelerator rather than the model. For exact checks rule that out, and a build is accepted only on exact agreement. An independent pure Python implementation of F reproduces the GPU per input per output program counts byte for byte. Stored entries decode their witness programs and re-execute it on exact CPU semantics, so every recorded behavior is a real, rerunnable program. The program index is re-enumerated and checked for identity of the exact set of program identities, not just their count. And the served posterior is byte identical to the exhaustive joint. Pre-release audit recomputed every frozen target from independent code paths and caught two builder defects that were invisible to the every accuracy style metric. So we have three tests of families, each with exact references. In induction, a hidden program is shown through input-output examples, and the model predicts its output on a held-up query against the exact posterior over outcomes. In continuation, the output is revealed one token at a time, and the model gives its next token distribution over 0, 1, and n against the exact condition at every position. In abduction, the model infers which of 8 candidate inputs produce a revealed output. Models are scored on the first two because those read off token log probabilities, which is what survey interfaces expose. Abduction is the sharpest discriminator of the three, but scoring it needs a distribution over candidate outputs, which no interface exposes cleanly. So here it validates the design. That is a limitation, and the first thing a better harness would fix. Now the metric. We measure the Jensen-Shannon divergence between the model's distribution and the reference, which is bounded and symmetric and needs no smoothing. Raw divergence geometry compresses every predictor toward the top of its scale, so we anchor it to 3 exactly computable points. The worst possible predictor scores 0. The keystroke references uniform random stroke at every step scores exactly 1/2. The F reference scores 1. The math is piecewise linear with a deliberate kink at 1/2, so one number tells you which side of anchor a model sits and how much of the gap it closes. The keystroke reference is not uninformed. It's itself an algorithmic mixture, the one induced by a print-only machine with no loops. So position relative to 1/2 locates a model between a loop-free mixture and a loop-bearing one. Before scoring any language model, we have to establish that distance to this reference diagnoses anything. We score a ladder of predictions, from the reference Bayesian rule down to purely superficial heuristics on a family drawn from the machine's own declared mixture. Panel A is the exact base for expected log loss falls from 4 bits with no examples to about 1/100th of a bit by 8. Nothing can lie below that curve, and the reference sits at 0 regret by construction. Panel B is what matters, the marginal predictor output frequencies with the inputs ignored, in the natural formalization of pattern completion. It spikes to 17 bits of regret at a single example by confidently committing to an output the algorithmic Mac does not support, and still pay 2 bits at 12. Nearest input analogy stays around 13. None of them approaches the reference. At full budget, the two accumulating evidence families behave differently, and the difference is informative. In continuation, even an input-agnostic pool predictor stays within 0.12 bits of the reference, and a uniform next token guess within about 0.26. So continuation is a sensitive fidelity probe that a weak foil separator. It says precisely how far a distribution sits from a target, but not by itself whether inference happened. Abduction is the opposite. The reference entropy collapses from t bits toward 1.3 as evidence accumulates, so a prior-only predictor drifts away from the sharpening target, and greedy matching improves but never arrives. The pair covers both axes, and one scope node I keep repeating. This separation is established on realizable families drawn straight from the pair, whereas the panel is scored on curated test sets. Now, part 2 of the presentation. What happens when you point this instrument at 105 serving configurations of real language models? So here's the panel: 49 API rows, 30 open models on NVIDIA NIM, a dated OpenAI letter from GPT-4o in May 2024 onward, Google's Gemini and Gemma lines, xAI's Rock, and Anthropic's Claude rows, plus 56 local builds spanning quantization ladders, a parameter scale ladder, and a base instruct and reasoning triads. Because the reference is fixed, every run is measured against the same target, and the same model served two ways is directly comparable. Four nested populations recur. The panel is all 105 runs. 81 expose next token distributions, and only those get a fidelity score. 80 of them completed both score and families. One episode is itself a datum. An API model was retired mid-evaluation, its continuation phase permanently uncertainable. Rows measured through commercial APIs can become unrepeated overnight. This is the measurement made concrete. Pain away is the induction accuracy against the number of examples. The reference locks on quickly, 98% by 4 examples and exact by 5, while the panel rises slowly and plateaus at 0.62. Panel B is more telling. A single example moves the panel mean away from the reference. Models overcommit to one datum before slowly recovering, which is exactly the failure the files showed 2 slides ago. It is nearly universal. 69 of 81 runs, frontier rows included, are further from the reference after one example than after none. What is not is overcommitment to simplicity. Agreement with base optimal answers tracks truth accuracy to within 2 points at every shot. Models favor neither the outcome answer nor the truth. Note also the coloring by parameter count shows no gradient. This is the headline, and it is the association accuracy alone conceals. Of 81 runs with usable log probabilities covering 46 models, 78 runs and 45 of the 46 models score below the keystroke reference. So distributionally further from the algorithmic posterior than a uniform keystroke. The one exception sits at the anchor. And look at the horizon axis. Models reach up to 92% accuracy while clustering between the dashed lines, and the two axes are uncorrelated. The frontier is no exception. Every proprietary row lands below the anchor, and the current flagship pairs near seeding accuracy with a fidelity of 0.33 below the panel median. There's an efficiency reading too. Median sampling complexity efficient is 0.4, so the typical model burns about 2.5 times the minimum number of samples on texts it does so. Panel B localizes the failure across all 9 reviewed positions. And just one more number. Plurality vote over the API panel scores 0.93 above every individual row, so the panel is collectively complementary on answers. No vote converts sub-anchor posteriors into calibrated ones. Here are two others side by side, and the point is that they are visibly unrelated. Panel A is the anchored fidelity scale for the 46 models with usable log probabilities. Blue is API, orange is local. The dashed line is the keystroke reference, and the shaded band is the sub-anchor region, which is where essentially everything lives. One bar crosses it. Panel B is the final shot accuracy for every model, including the accuracy-only rows, whose serving exposes no usable log probabilities and which, therefore, cannot appear in panel A. Rank these models by the number you normally read, and you get a completely different list. That is a practical case for the instrument. It measures a nexus existing leaderboards do not see. One caveat I return to is that these orderings are kept by the termination coordinate. The keystroke reference is deliberately the weakest evidence-free predictor. So far question is what stronger classical nodes do. We score them through the identical pipeline. From above, the dataset's global output frequencies, one distribution ignoring the query, the examples and the position reach 0.6, and the best input agnostic predictor reaches 0.73. Both are above every model in the panel. Both, though, are built from the frozen reference themselves, so neither is achievable without the target. From below, KT estimators fitted on the visible prefix land at 0.41 and 0.45, and their per position divergences bracket the panel brand. That gives the most defensible form of the result, one that does not depend on the identity of the target. The panel sits between a loop-free algorithmic mixture and a loop-bearing one, and the level of low-order prefix statistics. Because every task carries its exact posterior, each wrong answer can be classified rather than only counted. 31% of wrong answers carry exactly zero posterior mass on the evaluated support. And we need to be careful. The support here is bounded in length and runtime, and the prompt discloses neither bound. So that is a statement about the evaluated hypothesis class, not a deductive error. What it does show is that those answers are not near misses within the scored class. A blunter symptom means no support of argument. 46% of the errors do not even have the right output length, and the errors have positive structure, the false structure. 41% are verbatim copies of a shown output, rising to 70% by 8 examples. Only 2.8% are the outcome answer. Meanwhile, on the consistent support, models undercommit badly, so they pay twice. This next result is actually one of the favorites we got during the paper because it's distribution free and needs no reference at all. In a realizable noiseless setting, consistent evidence never lowers the posterior mass of the truth under any prior. And once the surviving hypotheses agree on the query, the answer is frozen. A Bayesian can abandon a correct answer only while an imposter hypothesis it prefers is still alive, never after identification. The reference shows exactly the lawful profile: 46 revisions against 406 learners at all the first or second example, and every one repaired by the final shot. The panel is qualitatively different. Across 98 complete runs, more examples produce 6,500 solved-to-unsolved transitions against 13,700 gains, and a quarter of the ever solved pairs end wrong. It's uncorrelated with accuracy and it tracks post-training in both triads. So what moves this gap? We ran controlled comparisons on three interventions that most improve conventional benchmarks. Quantization is benign for most of the panel. Four of the six letters are flat in both facets down to 1.7 bits per weight. Where this bite is accuracy that breaks, not fidelity. Our expectation had been the opposite, actually. In hindsight, the explanation is simple. A distribution already far from the reference has little further to fall, whereas the arc maximum accuracy reads off is exactly what the low bit quantization perturbs. Scale rises accuracy but barely moves fidelity, and post-training moves it the wrong way. In both families that ship all three stages at meshed side, the base model is the most faithful and instruction tuning lowest it, with non-overlapping intervals. Alignment sharpens distribution towards the answer format and away from the algorithmic prior. Parameter count is one axis along which capability grows. Release date at Frontier Laboratory is another, and it folds in every ingredient of the progress at once. Data, architecture, post-training, and scale. Because OpenAI still exposes the token log probabilities, we evaluated a data ladder of 9 models from GPT-4o in May 2024 through GPT 5.6 on the identical harness. Fidelity does not improve with frontier time. The oldest model is the best, and it also has the highest answer accuracy in the entire panel. Every later release sits in a band from 0.27 to 0.37. Two caveats bound to reading. 9 releases support no trend statistic, and 2 years of different serving routes, which we cannot control for. The conservative statement is no improvement in fidelity across 2 years, as served through the models that expose distributions. This is the light I'd like most of the community to act on. A benchmark that scores server distribution depends on providers expose them, and direct probes of the 4 frontier laboratories in July 2026 show that dependency is now precarious. OpenAI is the only laboratory still returning token log probabilities for its newest models. Google has withdrawn them at the frontier, and its compatibility layer stripped them from every model it hosts, third-party ones included. XAI accepts the parameter and silently returns nothing. Anthropic never exposed them. Silent omission is exactly the failure mode a degeneracy audit exists to catch. Then there is a safety layer, which is now part of the serving stack. One row's content filter refuses 16% of plain binary string induction carries, peaking in the ambiguous evidence region, and the same line sibling refuses every other carry and cannot be measured at all. One lever does improve fidelity, and it's the one nobody tells: evidence within test. The headline aggregates over all evidence levels, so we recompute the anchored score on cells with at least a minimum amount of evidence, with anchors recomputed on the same cells so both branches stay exact. On induction, on the left, the panel mean rises from 0.1 to 0.49, and the number of rungs above the anchor rises from 1 of 81 to 25. The crossers concentrate in the newest model families. Two bounds on that reading. The late cutoff estimate rests on cells where the posterior has not yet collapsed, so intervals widen and the mean stays below one half at every cutoff. On continuation, the picture is flat at every depth. The termination is calibration does not fade with evidence. And now we have the part three, which is the part where we describe what actually our results license. So what happens and what survives if there is a concern about the prior? So absolute distances, anchored scores, and model orders are properties of the chosen reference and need not survive an arbitrary change of machine or prior. We do not claim otherwise, and that descriptions of only tens of bits and various constant is not negligible. So we prove two statements that hold for rival priors. First, on a genuine sequential review, any predictor whose prior gives the computable reference positive weight has a bounded cumulative excess log loss. Second, this never invokes the reference at all. Any deterministic Bayesian mixture assigned positive mass to a realized truth has a bounded cumulative truth loss budget. The value is that the argument stops running through our numbers. If you reject our prior but hold any coherent prior that covers the truth, you owe a finite budget, and we can measure how much of it the observed paths have already spent. Here is what those bounds by empirically. For every history, we take exactly the distribution of the benchmark recorded, folded onto three classes and normalized. That deterministic map is itself a coherent predictor. So we computed pathwise identities for all 80 configurations and nearly 24,000 configurations for lecture pairs with no sampling law assumption. At the stop endpoint, 30% of the paths already require a finite covert penalty over 10 bits. The reference-free truth budget is larger. 87% of the paths exceed 10 bits and 39% exceed 20. We report full threshold survival curves, so no ceiling selected after seeing the data, with simultaneous bands from the cross-cluster resampling. Those bands are wide and they narrow the claim honestly. Because the horizon is 9 positions, there are lower bounds on what the rival prior must already pay. I want to be explicit about the three places where we corrected our headline. First, the score measures posterior fidelity, not predictive skill on a sample. Our tests are correlated, so evaluated law is not the prior, and 39 of the 80 scored runs predict the realized data better than the reference does. Below the anchor, therefore, cannot be read as worse than making no inference. Second, 89% of the raw continuation divergence is termination coordinate, and that is where curation bites hardest, because the shortest sample output has length 3. Third, undoing the length quota leaves the count unchanged, and scoring only the bit coordinate, and half the quota cannot distort. Still leaves 69 of 80 below the corresponding anchor, at about a third of the raw size. But the bit coordinate does not reproduce the ranking. So, the remaining boundaries are part of the design, and I would rather state them than leave them unannounced. At this budget, the prior reaches counting, arithmetic, and boundary recursion, not the full richness of universal computation. This is a clean probe at small description length, not a proxy for open-ended reasoning. The most important missing control is generator disclosure. Our prompt never names the machine, the prior, the budget, or the curation law. So distance to the reference confounds inferential components with knowledge of an unshared convention. Our promulgation is not the experiment. A decisive follow-up needs the three first registered arms, and it's the first control we intend to run. Two smaller ones. Scores are conditional on the prompt format, and note the direction, since breaking a model's format improves its score. So the failure model inflates our numbers rather than deflating them. Across a heterogeneous panel, the findings are consistent. Models select answers well above chance, but their predicted distributions sit at or below the keystroke reference, below a frequency lookup table, and at the level of a low-order prefix statistics. A single example makes nearly every model worse before it gets better. A large share of errors is inconsistent with the benchmark support for the shown evidence. None of the libraries that improve conventional benchmarks closes the gap, not scale across T orders of magnitude, not 2 years of frontier releases, and not post-training, which widens it. Two conditions bound all of that. The gap is the distance from the algorithmic posterior, not a claim that models predict the curated sample poorly. And the orderings are carried by the termination coordinate. What I would like you to take away is the instrument rather than the ranking. So FICOL is released as an open benchmark and toolkit. The enumeration is frozen once into a self-contained dataset, so evaluating a model costs only its own inference. The pipeline regenerates fresh test sets cheaply, which is our standing remedy against contamination. And every test is executable. The certified witness programs let you show the exact program a model failed to infer. Because the reference is explicit, it can serve as a training target and not only an evaluation. Thank you very much, and I'm really happy to take questions, and you can reach me through my emails, which are presented on the screen. Thank you again, and it was really good to be able to present this talk to this audience, and I hope this in-context learning studies keep on going because I think they're really important to the field. Thank you.